Today we will be doing nuclei. We all know that the nucleus of an atom consists of neutrons and protons, and collectively these are called nucleons. Now, in any atom, if the number of neutrons is denoted by N and if the number of protons is denoted by Z, then nuclei which are stable can be broken into two categories. A light stable nucleus has N by Z approximately equal to 1, and a heavy stable nucleus has N by Z approximately equal to 1 by 6. So those nuclei which have very low mass number and which are stable, their N by Z ratio is nearly 1, and those nuclei which have very high mass number and they are stable, their N by Z ratio is approximately 1.6. Nuclei which do not fall into either of these two categories, they can be categorized as unstable nuclei. So an unstable nucleus is one which doesn't fall into either of these two categories, and therefore it has either excess protons or excess neutrons. So to achieve stability, there will be nuclear disintegration and neutrons may convert to protons or vice versa. So this phenomenon is called radioactivity. So radioactivity refers to disintegration of the nucleus which is unstable so that it can achieve stability. Now, this entire topic is dealing only with nuclei. So first we need to get an idea about the size of a nucleus. The radius of any nucleus is given by the formula R is equal to R0 a to the power 1 by 3. A is the mass number of the nucleus, and R0 is a constant whose value is 1.1 into 10 to the power minus 15 meter, which is also written as 1.1 femtometer. So once you know the mass number of any nucleus, the radius of that nucleus can be calculated by this formula. As it's very clear that the size of a nucleus is in the range of femtometer. Now when nucleons are at separation in the range of femtometer, a force called nuclear force comes into play. So nuclear force comes into play whenever the protons and neutrons are at a separation in the range of femtometer. Nuclear force doesn't depend on charge. You know neutrons are chargeless. So neutrons, protons are bound to each other by nuclear force. So basically what happens is that if you take nucleons at infinity, suppose you take nucleons which are at infinity and you bring them to a separation in the range of femtometer to form the nucleus. So what will happen is that when they are brought together to form the nucleus, then the energy that is released, that energy is used to bind them together by nuclear force. So initially the neutrons and protons are at infinity, and from there they are brought close enough to form the nucleus. When the nucleus is formed, the energy that is released during the movement from infinity to the nucleus That released energy is responsible for the binding of the protons and neutrons by nuclear force. Nuclear force is much stronger than gravitational force, much stronger than Coulombic electrostatic force. And this is very, very important, that it only operates when the nucleons are in the range of femtometer. Now, I was telling you that when the nucleons are at infinity, and from there when they are brought close enough to form the nucleus, there is energy released. Now the question is, why is the energy released? Why is energy released when the nucleons are brought from infinity to form the nucleus? The reason is that if you note down the masses of all the protons and all the neutrons, suppose the mass of each proton is mp, the mass of each neutron is mn, so total mass of protons plus total mass of neutrons minus the mass of the nucleus into c square is the energy released. So the reason why energy is released is because of this phenomenon, which is known as mass defect. So the neutrons and protons, when they are brought from an infinite separation to form the nucleus, there is a mass defect. That means there is a loss of mass. When they were at infinite separation, the total mass of all of them was found to be greater than the mass of the nucleus which was formed. And this mass defect into c square is the energy released, and in fact this released energy is called binding energy of the nucleus. So the definition of binding energy is that it is the energy released during the formation of nucleus by aggregating the neutrons and protons from an infinite separation to form the nucleus. Now, binding energy is a very fundamental attribute of any nucleus, because this is the value which helps us to understand whether the nucleus is stable or not. Let us see how. See, there is a important graph. Y-axis is binding energy per nucleon and x-axis is mass number. So in the x-axis we have mass number, in the y-axis we have binding energy per nucleon. Now the thing is, this graph, the shape of the graph is approximately like this, and in this graph the elements whose mass number is between 50 to 80, they seem to be having the maximum binding energy per nucleon. In fact, the peak of this graph corresponds to iron. This is the peak of the graph. The binding energy per nucleon of iron is 8.7 mega electron volt. The binding energy per nucleon of deuteron. Deuteron is a hydrogen isotope with mass number 2. It is 1.11 mega electron volt. So you can see that the binding energy per nucleon of a very light nucleus like deuteron is very low, and a nucleus such as iron is very high. Not only that, all atoms, all nuclei whose mass number is between 50 to 80, they have very high binding energy per nucleon. Now you will notice one thing, that as you go higher and higher, let us say you go to uranium. Uranium mass number is 238. you will find that the binding energy per nucleon will become lower than the stable value. In fact, it becomes 7.5 mega electron volt. Now this graph is very important because it tells us a couple of things. First of all, when you have a very light nucleus like deuteron, its binding energy per nucleon is very low. So to achieve stability, it will try to aggregate or fuse with similar nuclei so that the overall mass number can increase and it can achieve stability. On the other hand, if you have a nucleus like uranium whose mass number is very high, it will disintegrate to give lighter nuclei to achieve stability. So the process by which a very light nucleus will combine with similar nuclei to achieve stability is called fusion, and the process by which a very heavy nucleus will disintegrate to form lighter nuclei is called fission. So fusion and fission are two processes of radioactivity which can take place spontaneously. In nature, there are many examples of spontaneously radioactive elements. It can also be triggered by human intervention. For example, in a nuclear reactor, we allow fission to take place to produce nuclear energy. Likewise, fusion also can happen spontaneously. For example, in the sun and the stars, nuclear fusion is the cause of the energy that is created. So this graph is very important, and all the features of this graph have to be kept in mind to analyze the stability of a nucleus. Now, since the topic is radioactivity, we are going to discuss types of radioactive decay. That's going to be our next topic. Types of radioactive decay. First is alpha decay. In alpha decay, what happens? The parent nucleus suppose its name is X, it disintegrates to give what we call the daughter nucleus Y, and helium nucleus is known as alpha particle. This is actually helium nucleus and we call this alpha particle. As you know, all such reactions are accompanied by a mass defect. So the calculation for mass defect will be like this: the mass of X minus the mass of Y minus the mass of the alpha particle. So alpha decay, what happens is that the mass of X is greater than the total mass of Y and the alpha particle, and this mass defect into C square is called the Q value of the reaction. So the Q value of a nuclear reaction is basically the energy that is available to the products. So in this case, products means the alpha particle, because the alpha particle will be moving with a certain kinetic energy. So that kinetic energy will come from the Q value of the reaction. Now this is important to note that in a particular decay scheme, all the alpha particles will have the same kinetic energy. It will be shared by all the alpha particles. The Q value will be shared by all the alpha particles which are coming out. So this is alpha decay. And you might have seen that the balancing of atomic numbers Z, Z minus 2 and 2, A minus 4 and 4. So this reaction from the point of view of mass number and atomic number is completely balanced. The next topic is beta decay. So one of the things which we spoke about earlier is the conversion of neutron to proton and vice versa. Now, suppose a neutron gets converted to a proton. Now, X is the parent nucleus, Y is the daughter nucleus. I told you a neutron has got converted to a proton. So you will see that X and Y have the same mass number, but the atomic number of Y is equal to atomic number of Z plus 1. Why? Because we now have one extra proton. Now this particle is called a beta particle. A beta particle is essentially an electron. In fact, you can also represent beta particle like this. It is essentially an electron, but very fast moving electron. And unlike electrons which are intrinsic to an atom, beta particle comes about only as a result of nuclear disintegration. Beta particle has no existence other than the fact that it comes about as a result of radioactive nuclear disintegration. Apart from beta particle, you also have a particle called antineutrino. Antineutrino does not have any charge or mass, so we cannot actually consider the antineutrino for the mass number and atomic number calculations. So you can see that the mass number and atomic number is between X, Y and the beta particle. Antineutrino is carrying energy, and that energy which comes from the Q value, which you have seen earlier, is shared by the antineutrino and the beta particle. So the Q value of this reaction is equal to the mass of X minus the mass of Y, the difference into C square. This is the Q value of the reaction. So this Q value is shared between the beta particle and the antineutrino. Now have a look at this reaction. This is an example of a proton getting converted to a neutron. The mass number AA, atomic number Z and Z minus 1. So proton is getting converted to neutron, and in the process you are releasing a beta plus particle. This is called a beta plus particle. Beta plus particle is exactly identical to electron, but it carries a positive charge. And this particle is called a neutrino. Now one important thing is that an antineutrino and a neutrino are so called because they are antiparticles of each other. In quantum physics, there are pairs of antiparticles, like for example, if a neutrino and an antineutrino collide with each other, if there is a collision between a neutrino and antineutrino, both of them will be completely destroyed and energy will be created. So whenever a neutrino and an antineutrino collide with each other, they destroy each other completely to create energy. So that is why this pair, they are called antiparticles. Similarly, a beta particle and a beta plus particle are also antiparticles of each other. So they will completely destroy each other to create energy. Now, in this case, the Q value of the reaction is given by this is the expression for the Q value of the reaction, the mass of X minus mass of Y minus twice the mass of electron. Now this into C square. Now this Q value is again shared between the beta plus and the neutrino. The beta plus particle and neutrino, they share the Q value. So that means in any beta decay or any beta plus decay, all the beta particles do not have the same energy because it is shared with the neutrino or the antineutrino. Incidentally, beta plus particle is also called positron because positive electron. It is similar to an electron but it is positive, so it is also known as a positron. Then the third kind of decay is called gamma decay. Now what happens is that whenever parent nucleus gets converted to daughter nucleus, the daughter nucleus, when it is formed, is in an excited state. So from the excited state, it will try to reach the ground state, and in order to do so, it will emit photons of gamma rays. Gamma rays are photons of extremely low wavelength, and they come about as a result of the transition of the daughter nucleus from excited state to ground state. So gamma rays cannot be shown by a nuclear reaction in this manner. You can only show it to be coming about as a result of the stability of the daughter nucleus. It is unstable, and to become stable it emits gamma ray photons. So this is how gamma decay takes place. All radioactive decay schemes follow chemical kinetics of first order. According to Madame Curie, if at a time t in a certain sample of radioactive substance, if at a time t the number of active nuclei is n, then in further time dt the number of nuclei which will disintegrate is given by dn is minus lambda into n into dt. So this is known as the law of radioactive decay. So this law can also be written like this: dn by n is minus lambda dt. Suppose you integrate both sides. So the number of nuclei you have to integrate from n0 to n, and time you have to integrate from 0 to t. So ln n by n0 is equal to minus lambda t. So n will be n0 into e to the power minus lambda t. So this is the law of radioactive decay, and this is another form of the same law which we can use for solving problems. Now, in the law of radioactive decay, the term minus dN by dt is called the activity of the sample, and you can see that activity is basically a measure of disintegrations per second. Activity is a measure of number of disintegrations per second. Now, number of disintegrations per second is called 1 becquerel, and the symbol is BQ. So the activity of any sample is measured in becquerel. 1 becquerel is 1 disintegration per second. The problem with becquerel is that as a unit it is too small. So we need a bigger unit, and that is 1 curie. So 1 curie, its value is 3.7 into 10 to the power 10 becquerel. So this is the preferred unit to measure the activity of a sample. The symbol for curie is CI, capital C, small I. This is the symbol for curie. Now there is another version of the law of radioactive decay in terms of activity. At any point of time, the activity of the sample is given by A is equal to A0 e to the power minus lambda t. So this is the formula to find the instantaneous activity of a sample. Since radioactive decay follows first order chemical kinetics, so like first order chemical kinetics, we can find the half-life. So how do you find the half-life? You just put n equal to half n0. If you put n equal to half n0, you will find that the time is coming ln2 by lambda. ln2 is approximately 0.693. So the time for half of the nuclei to disintegrate is 0.693 by lambda, and this time is known as the half-life. So just like in chemical kinetics, here also you can calculate the half-life in this manner. Now the thing is, there is another calculation called average life. It's more convenient to calculate the half-life because you can see from the nature of the law that the radioactive sample will take an interminably long time to completely disintegrate. So half-life is found to be a very useful calculation, but sometimes we also calculate the average life. How do we calculate the average life? Let us say at a time t, the number of available nuclei is n. Now after a time dt, the number of nuclei will become this. Why? Because you know, according to the law of decay, that in time dt the number of nuclei which decay is lambda n dt. So at time t, if the number of nuclei is n, then at time t plus dt the number of nuclei is this. That means that we can say that lambda n dt into t is the total life of the nuclei which have decayed during this time interval. Once again, we can say that lambda n dt into T is the total life of those nuclei, which means these nuclei which have decayed during this time. So in order to find the total life of all the nuclei, you will have to integrate this expression from 0 to infinity. So you replace n with n0 e to the power minus lambda t, and after you integrate by parts, the answer comes n0 by lambda. So you will have to do this integration by parts. Once the integration comes, the total life will be n0 by lambda. So the average life will be 1 by lambda. So this is the formula for average life. Usually, like I said, we use half-life, but sometimes average life is also used, and this is the formula. Average life is equal to 1 by lambda. Okay, now we will discuss comparison between alpha, beta and gamma rays. That is the next topic, comparison between alpha, beta and gamma rays. First of all, the speed. Now the thing is that in terms of speed, alpha is the slowest and gamma is the fastest. So usually the speed of alpha is in the range of 10 to the power 6 meter per second, and the speed of gamma is in the range of 3 into 10 to the power 8 meter per second, and beta is in between. Second is penetrating power. Now penetrating power follows the order alpha less than beta less than gamma. So the maximum penetrating power is that of gamma and the least is that of alpha. Third is ionizing power. Now ionizing power is maximum for alpha. Alpha particle is a doubly ionized helium nucleus, so it has high charge. Beta is small in size and the charge is also lesser than alpha. Gamma particles do not have any charge at all, so that's why the capability of alpha, beta, gamma to ionize the medium through which they are passing follows the order alpha greater than beta greater than gamma. Now alpha and beta can be deflected by electric magnetic fields, but not gamma. So gamma rays cannot be deflected by electric and magnetic fields. Alpha and beta rays can be deflected. Again, the reason is because they have a charge, whereas gamma rays do not have any charge. All three of them cause scintillation on striking a fluorescent screen. So all three of them cause scintillation on striking a fluorescent screen. So there are certain materials like barium platinocyanide, for example. So barium platinocyanide is a fluorescent material. So if alpha, beta, gamma rays fall on barium platinocyanide, they can cause scintillation. So these are the various properties of alpha, beta and gamma rays. Okay, now we come to the next topic, that is nuclear fission. Now we come to the next topic, that is nuclear fission. I was telling you earlier that when a heavy unstable nucleus like uranium wants to achieve stability, it can disintegrate to lighter nuclei. Now this disintegration is not always spontaneous. It was found that if you bombard uranium with slow moving neutrons, then that bombardment triggers the fission. Now when the fission takes place, the uranium disintegrates to give lighter nuclei, but it does not follow a pattern. In one decay scheme, you may have uranium giving iodine and yttrium. In another decay scheme, you may have uranium giving barium and krypton. So in both cases, you are bombarding the uranium with slow moving neutrons, and after the fission reaction is over, some more neutrons are emitted. Now the problem is that these neutrons which are emitted, their energy is in the region of 2 mega electron volt, whereas the neutrons which are used to bombard the uranium, their energy is in the region of 1 to 100 electron volt. So the neutrons which are emitted during fission, their energy is very, very high, whereas the neutrons which are required to initiate the fission, their energy is in this range. So what we can do is, if we can ensure that these neutrons which are emitted, their energy can be brought down by some method, then those neutrons can be used to continue the nuclear fission. So once we have got the highly energetic neutrons, if we can bring down their energy to this region, then we can use it to continue the fission. In fact, in that case, it is called a chain reaction, because it continues as long as there are enough neutrons to trigger the fission. This is the typical layout of a nuclear reactor. In a nuclear reactor, the uranium, which is the fissile material, is kept in the form of rods. So you can see these uranium rods. Now, there are some control rods. These control rods act like a switch to start and stop the nuclear reaction. Now there is dense packing of a substance called moderator. Now moderator, the options are you can use heavy water, or you can use graphite, or you can use beryllium. So these are the preferred moderators. What does a moderator do? You see the neutrons which are coming out of the fission, their energy has to be brought down, which I told you earlier. So to bring down the energy, we need a dense packing of moderator. Moderator's job is to bring down the energy of the neutrons to the region of 1 to 100 electron volt. So that is why there is a packing of moderator. Now when the reaction is taking place and at some point of time the reactor has to be shut down, then what we do is we push the control rods into the reactor to adequate depth, and once they are pushed in for up to an adequate depth, the reaction completely stopped. So control rods are made up of substances which are very good neutron absorbers, and in fact the most common one is cadmium. So cadmium is a very good neutron absorber. So the control rods are made up of cadmium to completely absorb the neutrons. As you know that all nuclear reactions are accompanied by a mass defect. So due to the mass defect, there will be an enormous amount of energy released. That released energy can be used to convert water to steam. So by means of a pump, we will pass cold water into the reactor, and hot water will come out after taking the energy from the nuclear reaction. And this hot water in turn can be used to produce steam, and this steam is then used to run a turbine and produce electricity, right? So this is how the entire reactor works. So the essential feature in a nuclear reactor is that it is a nuclear fission chain reaction which is triggered by the slow moving neutrons. To slow down the neutrons we use moderator, and to start or stop the reactor we use control rods. If you pull them out, the reaction starts. If you push them in, the reaction stops. Control rods are typically made up of very good neutron absorbers such as cadmium. Once the reaction takes place, enormous amount of heat is liberated due to the nuclear energy, and that heat is used to convert water to steam, and the steam is then used to run a turbine and produce electricity. Next we come to nuclear fusion. You see the temperature in the sun of our solar system is in the range of 1.5 into 10 to the power 7 Kelvin. the temperature in the sun is very, very high. Now what happens is that at this high temperature, the atoms are completely stripped of their electrons. For example, if you are considering a hydrogen atom, it is completely stripped of this electron due to the high temperature. Now, once the atom is stripped of this electron, then the nucleus is able to approach a similar nucleus of another atom. For example, let's say this is another hydrogen. So they have lost their electron due to the high temperature, and now the two nuclei are able to come to close proximity and fuse with each other. So that fusion typically takes place as follows. You can see that there is a neutrino positron and there is a deuteron. Again, a deuteron may combine with another hydrogen to give a nucleus whose mass number is 3, a helium nucleus with mass number 3, and two such nuclei will combine together to give a alpha particle. So the overall reaction from start to finish is basically combination of 4 hydrogens to produce one alpha particle. So this is the reaction which takes place in the sun, and this reaction is also known as proton-proton cycle. So proton-proton cycle is the reaction which takes place in the sun. It occurs by the combination of 4 hydrogen atoms to give a helium nucleus, and a large amount of energy is released in the process. Now, there are many stars whose temperature is even higher. So, in very, very hot stars, the temperature is in the region of 10 to the power 8 Kelvin. Now what happens is that the reaction in hot stars is ultimately the same, but carbon acts like a catalyst. So you will see that carbon will appear at various steps, but the end reaction is the same. So you can see that it starts with a hydrogen atom, and with the initiation of carbon you are getting nitrogen, again carbon 13, and then nitrogen 14, oxygen 15, nitrogen 15, and finally you are getting alpha particle. So you can see that the end reaction is the same. 4 hydrogens are combining to give a alpha particle and release huge amount of energy. So this cycle is called proton carbon cycle. So the end result is the same, but the carbon is playing the role of a catalyst. So this is how nuclear fusion reactions can take place in hot stars. So that brings us to an end of this particular topic, that is nuclei.